Today's video lesson is on sampling distributions. In this section, we'll look at parameters and statistics, what is a sampling distribution, distinguish between a population distribution, sampling distribution, and distribution of sample data, determine whether statistics is an unbiased estimator of a population parameter, and describe the relationship between sample size and variability of an estimator. The process of statistical inference involves using information from a sample to draw conclusions about a wider population. Different random samples yield different statistics. We need to be able to describe the sampling distribution of possible statistic values in order to perform statistical inference. We can think of a statistics as a random variable because it takes numerical values that describe the outcomes of the random sampling process. Therefore, we can examine its probability distribution using what we learned in Chapter 6. We collect data from a representative sample, make an inference about the population based on this representative sample. As we begin to use sample data to draw conclusions about a wider population, we must be clear about whether a number describes a sample or a population. A parameter is a number that describes some characteristic of the population. In statistical practice, the value of a parameter is usually not known because we cannot examine the entire population. A statistic is a number that describes some characteristic of a sample. The value of a statistic can be computed directly from the sample data. We often use a statistic to estimate an unknown parameter. Remember, S statistics come from samples and P parameters come from populations. We write the Greek word mu for the population mean and x bar for the sample mean. We use P to represent a population proportion. The sample P hat is used to estimate the unknown parameter P. When defining a parameter, use phrases like population mean or true mean rather than simply saying mean, which can refer to the mean of a population or the mean of a sample. Examples: heights and cell phones. Identify the population, parameter, sample, and the statistic in each of the following settings. A pediatrician wants to know the 75th percentile for the distribution of heights for 10-year-old boys, so she takes a sample of 50 patients and calculates Q3 equals 56 inches. B. A Pew Research Center poll asked 1,102 12 to 17-year-olds in the United States if they have a cell phone. Of the respondents, 71% said yes. So here's our solutions. The population in the first example is 10-year-old boys. The parameter of interest is the 75th percentile, or Q3. The sample is the 50 10-year-old boys included in the sample. The statistic is the sample Q3 equals 56 inches. The population in the second one is all 12 to 17-year-olds in the U.S. The parameter is the proportion with cell phones. The sample is the 1,102 12 to 17-year-olds in the sample. The statistic is the sample proportion with a cell phone, which was P hat equals 0.71. This basic fact is called sampling variability. The value of a statistic varies in repeated random sampling. To make sense of sampling variability, we ask, what would happen if we took many samples? How can x bar be an accurate estimate of mu? After all, different random samples will produce different values of x bar. A deck of cards with aces and face cards removed, so that only the cards 2 through 10 remain, is shown. Each student shuffles the deck, randomly selects 5 cards, and notes the median value of the cards. For example, if the selected cards were 2, 2, 4, 5, and 9, the median would be 4. Each student records the value of the sample median on a class dot puck dot plot going from 2 to 10. We simulate choosing 500 simple random samples of size 5 from the deck of cards. The graph shows the distribution of the sample median for these 500 samples. Is this the sampling distribution of the sample median? No. Since the distribution didn't use all possible samples of size 5, this isn't the exact sampling distribution. Are there any obvious outliers describing the distribution? First, we describe shape. The graph is roughly symmetric with a single peak at 6. Center. The mean of the distribution is about 6. Spread. The values fall mostly between 4 and 8, although there are values as low as 2 and as high as 10. Outliers? There don't seem to be any outliers. Suppose another student prepared a different deck of cards and claimed it was exactly the same as the one used in the activity. However, when you took a simple random sample of size 5, the median was 4. Does this provide convincing evidence the student's deck is different? Getting a sample median of 4 does not provide convincing evidence that the student's deck is different. Getting a sample median of 4 or lower occurs fairly often just by chance when taking random samples of size 5 from a deck of cards with the aces and face cards removed. In a previous activity, we took a handful of samples of 20 chips. There are many possible simple random samples of size 20 from a population of 200. If we took every one of those possible samples, calculated the sample proportion of each, and graphed all of these, we'd have a sampling distribution. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. In practice, it's difficult to take all possible samples of size n to obtain the actual sampling distribution of a statistic. Instead, we can use simulation to imitate the process of taking many samples. One of the uses of probability theory in statistics is to obtain sampling distributions without simulation. There are actually 3 distinct distributions involved when we sample repeatedly a measure a variable of interest. The population distribution gives the values of the variable for all the individuals in the population. The distribution of sample data shows the values of the variable for all the individuals in the sample. The sampling distribution shows the statistic values from all possible samples of the same size from the population. So the population distribution gives the values of the variables for all the individuals in the population. Our individuals here are 200 chips. Variable is a color. Parameter, proportion of red chips, that's our color red chips, in the population is 0.5. Each random sample equals 20 chips. Here's a sampling distribution of what it might look like. Here's the parameter of blue and red chips. If we have 2 different colors, each one has a probability of 0.5 or 50%. If we then take distributions of sample data and do simple random samples of 20, here's what we might find. When we put this into a sampling distribution, here's what it'll look like. Wording is important. You cannot say the variability decreases when the sample size increases, for example. This may be true for the distribution of a sample statistic, but it is not true for the distribution of the sample. When describing a distribution, say, the distribution of whatever it is to avoid losing points. Don't say sample distribution when you mean sampling distribution. The population distribution and distribution of sample data describe individuals. A sampling distribution describes how a statistic varies in many samples from the population. The fact statistics from random samples have definite sampling distributions allows us to answer the question, how trustworthy is a statistic as an estimator of the parameter? To get a complete answer, we consider the center, spread, and shape. Center, biased and unbiased estimators. In the chips example, we collect many samples of size 20 and calculate the sample proportion of red chips. How well does the sample proportion estimate the true proportion of red chips? P equals 0.5. The center of the approximate sampling distribution is close to 5. In fact, if we took all possible samples of size 20, found the mean of those sample proportions, we'd get exactly 0.5. A statistic used to estimate a parameter is an unbiased estimator if the mean of its sampling distribution is equal to the true value of the parameter being estimated. Unbiased doesn't mean perfect. Example, suppose the heights of adult males are approximately normally distributed with the mean of 70 inches and standard deviation of 3 inches. To see why sample size matters, we took 1,000 simple random samples of size 100 and calculated the sample mean height, and then took 1,000 simple random samples of size 1,500 and calculated the sample mean height. Here are the results graphed on the same scale for easy comparison. As you can see, the spread of the approximate sampling distributions is much different. When the sample size was larger, the distribution of the sample mean was much less variable. In other words, when the sample size is larger, the sample mean will be closer to the true mean on average. Low variability is better. To get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. This ensures that you won't tend to overestimate or underestimate. Unfortunately, using an unbiased estimator doesn't guarantee the value of your statistic will be close to the actual parameter value. Larger samples have a clear advantage over smaller samples. They are much more likely to produce an estimate close to the true value of the parameter. The variability of a statistic is described by the spread of its sampling distribution. This spread is determined primarily by the size of the random sample. Larger samples give smaller spread. The spread of the sampling distribution does not depend on the size of the population as long as the population is at least 10 times larger than the sample. Bias, variability, and shape. We can think of the true value of the population parameter as the bullseye on a target and the sample statistic as an arrow fired at the target. Both bias and variability describe what happens when we take many shots at the target. Bias means our aim is off and we consistently miss the bullseye in the same direction. Our sample values do not center on the population value. High variability means repeated shots are widely scattered on the target. Repeated samples do not give very similar results. Given a choice of statistics to estimate an unknown parameter, choose one with no or low bias and minimum variability. Sampling distributions can take on many shapes. The same statistic can have sampling distributions with different shapes, depending on the population distribution and the sample size. Be sure to consider the shape of the sampling distribution before doing inference. Sampling distributions for different statistics used to estimate the number of tanks in the German tank problem that we looked at, or will be looking at. The blue line represents the true number of tanks. Notice the different shapes. Which statistic is the best estimator and why? We'll take a look at this as we go through our lessons. Here's a summary of the lesson for today.